So welcome to the next subtopic in Level 3 NCEA Mechanics, momentum. And the special case compared to Level 2 is that we're looking now, instead of one dimension, looking at momentum in 2 dimensions. So why can't this giant oil tanker stop that easily? Well, it's twofold. It's very, very big, and it's also moving quite quickly. It has a lot of momentum. So remember from last year that momentum essentially is the mass of an object times its velocity. And again, this is quite useful when we're looking at collisions and explosions. Momentum is a vector quantity, okay, which means, of course, just like velocity, it has a direction and a magnitude, a size, and that means in order to have momentum, there has to be an unbalanced force acting on it to cause a change in velocity. Okay, so it also, if you're changing the velocity due to the equation, you're going to be changing the momentum of the object. And we're going to look at that more explicitly later in the video. Okay, so therefore, the change in momentum will be the final momentum minus the initial momentum. Quite straightforward. And also, we have the concept of the conservation of momentum, of course, from last year, where basically in a collision, the total momentum at the beginning of the collision will be the same as it is at the end, as long as there's no external forces acting. So it has to be a closed system. This is quite useful when it comes to working out calculations. So leading on from momentum, we have the concept of impulse. And impulse is basically when we're changing the velocity of an object, then it's going to accelerate, because acceleration is change of velocity over change in time. And this acceleration is caused via Newton's second law by an unbalanced force. So that means that the change in velocity results in a change in momentum. And this change in momentum is known as impulse. And we can see there how to gather that. So force, or net force, equals mass times acceleration from Newton's second law. And we know that acceleration is change in velocity over change in time. So therefore, if you substitute change in velocity over change in time into the first equation, into Newton's second law, then you get force multiplied by this change in time equals the mass multiplied by the change in velocity. Or if you then rearrange that, force equals change in time, or force times change in time equals a change in momentum, because we already know that momentum equals mass times velocity. So just like with force components, horizontal and vertical components for momentum can be conserved. Okay, so basically you're conserving momentum in the horizontal direction, and you can conserve momentum in the vertical direction. This comes in quite handy. Okay, so that means that all the horizontal components in a collision are going to be the same, at least in terms of vectors, as the horizontal components after the collision. Okay, and the same was also for the vertical components in a collision. Okay, you can see that from the diagrams on the slide in front of you, that before the collision, the horizontally x1 plus x2 equals x3, and then the resultant, therefore, using a bit of trig, is going to be x3 is going to be corresponding to plus y3 in the up direction. Okay, that's just using trig. Because vertically, y1 plus y2 is going to equal y3. And finally, for this short video, the same thing as we see with momentum, you're also going to be seeing in energy. Okay, so energy, not only momentum, is conserved. Thus, the energy before some sort of collision is going to be equal to the energy after the collision. Again, as long as there's been no kind of external force, as long as the system is closed. And the main energies we're going to look at in a little bit more detail, potentially, are kinetic energy, gravitational potential energy, the work done, and power.